All right, good morning. Let's get started. So today you see the support vector machine algorithm. And this is one of my favorite algorithms because it's very turnkey, right? If you have a classification problem, you just kind of run it and it more or less works. So in particular, talk a bit more about the optimization problem that you have to solve for the support vector machine. Then talk about something called the representer theorem. And this will be a key idea to how we'll work in potentially very high dimensional, like 100,000 dimensional or 1,000,000 dimensional or 100 billion dimensional or even infinite dimensional feature spaces. And this will teach you how to represent feature vectors and how to represent parameters that may be 100 billion dimensional or 100 trillion dimensional or infinite dimensional. Based on this, we derive kernels, which is the mechanism for working with these incredibly high-dimensional feature spaces, and then hopefully, time permitting, wrap up with a few examples of concrete implementations of these ideas. So to recap, on last Wednesday, we started to talk about the optimal margin classifier, which said that if you have a data set that looks like this, then you want to find the decision boundary with the greatest possible geometric margin, right? And so the geometric margin can be calculated via this formula, and this is just, the derivations in the lecture notes. It's just measuring the distance to the nearest point, right? And for now, let's assume the data can be separated by a straight line. And so gamma I this is sort of geometry, I guess, derivation in the lecture notes. This is the formula for computing the distance from the example xi, yi to the decision boundary governed by the parameters w and b. And gamma is the worst case geometric margin, right? You will make, of all of your M training examples, which one has the least or has the worst possible geometric margin? And the support vector, the optimal margin classifier, will try to make this as big as possible. And by the way, what you see later on is that optimal margin classifier is basically this algorithm, and optimal margin classifier plus kernels, meaning basically take this idea but apply it in a 100 billion dimensional feature space. That's the support vector machine. Okay. So I saw, one thing I didn't have time to talk about on Wednesday was the derivation of this classification problem. So where does this optimization objective come from? So let me just go over that very briefly. So the way I motivated these definitions was said that given a training set, you want to find the decision boundary parameterized by W and B that maximizes the geometric margin, right? And so again, as recap, your classifier will output G equals W transpose X plus B. And so you want to find parameters W and B. They'll define the decision boundary where your classification switch from positive to negative that maximizes the geometric margin. And so one way to pose this in an optimization problem is, is to try to find the biggest possible value of gamma subject to that the geometric margin must be greater than or equal to gamma, right? So in this optimization problem, the parameters you get to fiddle with are gamma, W, and B. And if you solve this optimization problem, then you're finding the values of W and B that defines a straight line, that defines the decision boundary. So this constraint says that every example, right? So this constraint says every example has geometric margin greater than or equal to gamma. This is what it's saying. And you want to set gamma as big as possible, which means that you're maximizing the worst case geometric margin. Does this make sense? Right? So the only way to make gamma, say 17 or 20 or whatever, is if every training example has geometric margin bigger than 17, right? And so this optimization problem is trying to find W and B to drive up gamma as big as possible and have every example have geometric margin even bigger than gamma. So this optimization problem maximizes it causes you to find W and B with as big a geometric margin as possible, as big a worst case geometric margin as possible. Okay. And so, does this make sense actually? Right? Okay. Actually, raise your hand if this makes sense. Oh, good. Okay. Well, many of you. All right. Let me see this in a slightly different way. So let's say you have a few training examples. In the training examples, geometric margins are 17, 2, and 5, right? Then the geometric margin in this case is a worst case value 2, right? And so if you are solving an optimization problem where I want every example, where I want where I want a min over I of gamma I to be as big as possible, one way to enforce this is to say that gamma I must be bigger than or equal to gamma for every possible value of I, and then I'm going to lift gamma up as much as possible, right? Because the only way to lift gamma up subject to this is if every value of gamma I is bigger than that. And so lifting gamma up, maximizing gamma, has the effect of maximizing the worst case example's geometric margin, which is how we've defined this optimization problem. Okay. And then the last one step to turn this problem into this one on the left is this interesting observation that you might remember when we talked about the functional margin, which is the numerator here, that the functional margin, you can scale W and B by any number, and the decision boundary stays the same. Right? And so, if your classifier is Y, so this is G of W transpose X plus B, right? So if, let's see, example I want to use 2, 1. If W was the vector 2, 1, let's say that's the classifier, right? Then you can take W and B and multiply it by any number you want. I can multiply this by 10, and this defines the same straight line, right? So in particular, I think, let's see, with this 2, 1x, this actually defines a decision boundary that looks like that. If this is x1 and this is x2, then this is the equation of the straight line where W transpose X plus B equals 0. Right? That's 1 and 2. You could verify for yourself. You plug in this point, then W transpose X plus B equals 0. You plug in this point, W transpose X equals 0. And so that's the decision boundary where the SVM will predict positive everywhere here, and it'll predict negative everywhere to the lower left. And this straight line, stays the same even if you multiply these parameters by any constant. Okay. And so to simplify this, notice that you could choose anything you want for the norm of W, right? Just by scaling this by a factor of 10, you can increase it, or scaling it by a factor of 1 over 10, you can decrease it. But you have the flexibility to scale the parameters W and B, up or down by any fixed constant without changing the decision boundary. And so the trick to simplify this equation into that one is if you choose to scale the norm of W to be equal to 1 over gamma, because if you do that, then this optimization objective becomes maximize 1 over norm of W subject to so if you substitute norm of W equals 1 of gamma, and so that cancels out And so you end up with this optimization problem. Instead of maximizing 1 over norm of W, you can minimize 1/2 the norm of W squared subject to this. Right? Okay. And so that's a rough, I know I did this relatively quickly. Again, as usual, the full derivation is written on the lecture notes, but hopefully this gives you a flavor for why, if you solve this optimization problem, and you're minimizing over W and B, that you are solving for the parameters W and B that give you the optimal margin classifier. Okay. Now, the optimal margin classifier, we've been deriving this algorithm as if, you know, the features xi, let's see. We've been deriving these algorithms as if the features xi are some reasonable dimensional feature, x equals R2, x equals R100 or something. What we will talk about later is a case where the features xi become, you know, 100 trillion dimensional, right, or infinite dimensional. And what we will assume is that W can be represented as a sum, as a linear combination of the training examples. Okay? So in order to derive the support vector machine, we're going to make an additional restriction that the parameters W can be expressed as a linear combination of the training examples, right? So, and it turns out that when xi is, you know, 100 trillion dimensional, doing this will let us derive algorithms that work even in these 100 trillion or in these infinite dimensional feature spaces. Now, I'm describing this just as an assumption. It turns out that there's a theorem called the representative theorem that shows that you can make this assumption without losing any performance. The proof of the representative theorem is quite complicated. I don't want to do this in this class. It's actually written out. The proof of why you can make this assumption is also written on the lecture notes. It's a pretty long and involved proof involving primal dual optimization. I don't want to present the whole proof here, but I'm going to give you a flavor for why this is a reasonable assumption to make. Okay? Oh, and just to make things complicated, later on, we actually do this, right? So yi is always plus minus 1. So we're actually, by convention, we're actually going to assume that wi can be written, right? So in this example, this is plus minus 1, right? So this makes some of the math a little bit downstream come out easier. But this is still saying that w can be represented as a linear combination of the training examples. Okay? So let me just describe less formally why this is a reasonable assumption, but it's actually not an assumption. The representative theorem proves that this is just true at the optimal value of W. But let me convey a couple ways why this is a reasonable thing to do or assume, I guess. So maybe here's intuition number 1. And I'm going to refer to logistic regression. Right, where suppose that you run logistic regression with gradient descent, say stochastic gradient descent, then you would initialize the parameters to be equal to 0 at first, and then for each iteration of stochastic gradient descent, right, you would update theta gets updated as theta minus the learning rate times, times xi, okay? And so, sorry, here alpha is the learning rate. Nothing, this overload the notation. This alpha has nothing to do with that alpha. But so just saying that on every iteration, you're updating the parameter theta as by adding or subtracting some constant times some training example. And so kind of proof by induction, right? If theta starts off 0, and if on every iteration of gradient descent, you're adding a multiple of some training example, then no matter how many iterations you run gradient descent, theta is still a linear combination of your training examples. Okay, and again, I did this with theta. It was really theta 0, theta 1, up to theta n, right? Whereas here we have b, and then w1 down to wn. Wow, this pen's really bad. I feel like, all right. Yeah, we should make sure to throw these away so they don't keep haunting us in the future. Okay, right. So, if you, so I did this with theta rather than W, but it turns out if you work through the algebra, this is a little bit of proof by induction that, as you run logistic regression, after every iteration, the parameters theta or the parameters W are always a linear combination of the training examples. And this is also true if you use batch gradient descent. Right? If you use batch gradient descent, then the update rule is this. Yeah, right. Okay, right. And so it turns out you can derive gradient descent for the support vector machine learning algorithm as well. You can derive gradient descent to optimize W subject to this, and you could have a proof by induction, that no matter how many iterations you run gradient descent, it will always be a linear combination of the training examples. So that's one intuition for how you might see that assuming W is a linear combination of the training examples, is a reasonable assumption. I want to present a second set of intuitions, and this one would be easier if you're good at visualizing high-dimensional spaces, I guess. But let me just give intuition number 2, which is, let's see. So, so first of all, let's take our example just now, right? Let's say that the classifier uses this 2, 1, x minus 2, right? So this is W, and this is B. Then it turns out that the decision boundary is this, where this is 1, and this is 2. And it turns out that the vector W is always at 90 degrees to the decision boundary, right? This is a fact of, I guess, geometry or something, or linear algebra, right? Where the vector W, 2, 1, so the vector W, is sort of 2 to the right and then 1 up, is always at, wow, all right. The vector W is always at 90 degrees to the decision boundary. And the decision boundary separates where you predict positive from where you predict negative, okay? And so it turns out that if you have, to take a simple example, let's say you have 2 training examples, a positive example and a negative example, right? Then by illustration, x2, right? The linear algebra way of saying this is that the vector W lies in the span of the training examples. Okay? Oh, and the way to picture this is that W sets the direction of the decision boundary, and as you vary B, then the position, so the relative position, setting different values of B will move the decision boundary back and forth like this, and W pins the direction of the decision boundary. Okay? And just one last example for why this might be true. So we're going to be working in very, very high dimensional feature spaces. For this example, let's say you have 3 features, x1, x2, x3, right? And later we'll get to where this is like 100 trillion, right? And let's say, for the sake of illustration, that all of your examples lie in the plane of x1 and x2. So let's say x3 is equal to 0. Okay, so let's say for all of your training examples, x3 equals 0. Then the decision boundary, will be some sort of vertical plane that looks like this, right? So this is going to be the plane specifying W transpose x plus B equals 0, where now W and x are 3-dimensional. And so the vector W should have W3 equals 0, right? If one of the features is always 0, is always fixed, then W3 should be equal to 0. And that's another way of saying that the vector W, should be represented as in the span of just the features x1 and x2, as a span of the training examples. Okay. All right, I'm not sure if either intuition 1 or intuition 2 convinces you. I think hopefully that's good enough. But the second intuition will be easier if you're used to thinking about vectors in high-dimensional feature spaces. And again, the formal proof of this result, which is called the representative theorem, is given in the lecture notes. But it's actually, I don't know, it's actually one of the most complicated. It's definitely on the high end in terms of complexity of the full derivation, of the formal derivation of this result. So, all right, so let's assume that W can be written as follows. So our optimization problem was this. You want to solve for W and B so that the norm of W squared is as small as possible, and so that this is bigger than or equal to 1, right? For every value of I. So let's see, norm of W squared, this is just equal to W transpose W. And so if you plug in this definition of W, into these equations, you have as the optimization objective min of 1/2 sum from I equals 1 through M. So this is W transpose W. Which is equal to, I guess, sum of I, sum over J, alpha I, alpha J, yi, yj, and then xi transpose xj, right? And I'm going to take this. So this is an inner product between xi and xj, and I'm going to use, I'm just going to write it as this, right? Xi, this notation, so x comma z equals x transpose z is the inner product between two vectors. This is maybe another alternative notation for writing inner products. And when we derive kernels, you see that expressing your algorithm in terms of inner products between features x is the key mathematical step needed to derive kernels. I'm going to use this slightly different sort of open angle brackets, closed angle brackets notation to denote the inner product between two different feature vectors. So that is the optimization objective. Oh, and then this constraint, it becomes something else, I guess. This becomes, what is it? Yi times W, which is transpose x plus b is greater than or equal to 1. And again, this simplifies, or if you just multiply this out, so just to make sure the mapping is clear, all these pens are like dying. All right, I'm just not. All right, so that becomes this, and this becomes that. Okay. And the key property we're going to use is that if you look at these two equations in terms of how we pose the optimization problem, the only place that the feature vectors appears is in this inner product. Right? And it turns out, when we talk about the kernel trick, when we talk about the application of kernels, it turns out that if you can compute this very efficiently, that's when you can get away with manipulating even infinite dimensional feature vectors. We'll get to this in a second. But the reason we want to write the whole algorithm in terms of inner products is there'll be important cases where the feature vectors are 100 trillion dimensional, but you can compute it, or even infinite dimensional, but you can compute the inner product very efficiently without needing to loop over, like 100 trillion elements in an array, right? And we'll see exactly how to do that later, very shortly. So, all right. Now, it turns out that we've now expressed the whole optimization algorithm in terms of these parameters alpha, right, defined here, and b. So now the parameters need to, now the parameters need to optimize for our alpha. It turns out that by convention, in the way that you see support vector machines referred to, in research papers or in textbooks, it turns out there's a further simplification of that optimization problem, which is that you can simplify it to this. And the derivation to go from that to this is, again, relatively complicated. But it turns out you could further simplify the optimization problem I wrote there to this. Okay. And again, you can copy this down if you want, but this is also written in the lecture notes. And by convention, this slightly simplified version of optimization problem is called the dual optimization problem. The way to simplify that optimization problem to this one, that's actually done by using convex optimization theory. And again, the derivation is written in the lecture notes, but I don't want to do that here. If you want, think of it as doing a bunch more algebra to simplify that problem to this one and coincidentally cancel out b along the way. It's a little more complicated than that, but right, a full derivation is given in the lecture notes. And so finally, the way you the way you make a prediction, right, is you solve for the alpha i's, and maybe for b, right? So you solve this optimization problem or that optimization problem for the alpha i's. And then to make a prediction, you need to compute h of w b of x for a new test example, which is g of w transpose x plus b, right? But because of the definition of w, this is equal to g of that's w transpose x plus b, because this is w. And so that's equal to g of sum over I, alpha I, yi, in a product between xi and x plus b. And so once again, once you have stored the alphas in your computer memory, you can make predictions using just inner products again, right? And so the entire algorithm, both the optimization objective you need to deal with during training, as well as how you make predictions, is expressed only in terms of inner products. Okay. So we're now ready to apply kernels. And sometimes in machine learning people, sometimes we call this a kernel trick. And let me just lay out a recipe for what this means. Step one is write your whole algorithm in terms of xi, xj, in terms of inner products. And instead of carrying the superscript, xi, xj, I'm sometimes going to write inner product between x and z, right? Where x and z are supposed to be proxies for two different training examples, xi and xj, but it simplifies the notation right a little bit. Two, let there be some mapping from your original input features x to some higher dimensional set of features phi. And so one example would be, let's say you're trying to predict, housing prices or predict if a house will be sold in the next month. So maybe x in this case is the size of the house, or maybe is size in, right. Maybe x is the size of a house. And so you could take this 1D feature and expand it to a high dimensional feature vector with x squared, x cubed, x to the 4, right? So this would be one way of defining a high dimensional feature mapping. Or another one could be if you have two features, x1 and x2, corresponding to the size of the house and the number of bedrooms, and you can map this to different phi of x, which may be x1, x2, x1 times x2, x1 squared, x2, x1, x2 squared, and so on, right? Kind of a polynomial set of features, or maybe other set of features as well, okay? And what we'll be able to do is work with feature mappings, phi of x, where the original input x may be 1D or 2D or whatever, and phi of x could be, 100,000 dimensional or infinite dimensional. But we'll be able to do this very efficiently, right? Or even infinite dimensional. Okay. So we'll give some concrete examples of this later, but I want to give you the overall recipe. And then what we're going to do is to find a way to compute k of x comma z equals phi of x transpose phi of z. So this is called the kernel function. And what we're going to do is we'll see that there are clever tricks so that you can compute the inner product between x and z even when phi of x and phi of z are incredibly high dimensional. Right? We'll see an example of this in very, very soon. And then step 4 is replace xz in algorithm with k of xz, okay? Because if you could do this, then what you're doing is you're running the whole learning algorithm on this high dimensional set of features. And the problem with swapping out x for phi of x, right, is that it can be very computationally expensive if you're working with 100,000 dimensional feature vectors, right? I mean, even by today's standards, 100,000, it's not the biggest I've seen. Actually, the biggest I've seen is actually like 1 billion features. But even by today's standards, 100,000 features is actually quite a lot. And if you're a large training set, just 100,000 is just a large number of features, I guess. And the problem of using this is it's quite computationally expensive to carry around these 100,000 or million dimensional or 100 million dimensional feature vectors or whatever. But that's what you would do if you were to swap in phi of x, in the naive, straightforward way for x. But what we'll see is that if you can compute k of xz, then you could, because you've written your whole algorithm just in terms of inner products, then you don't ever need to explicitly compute phi of x. You can always just compute these kernels. Yeah. Let me get to that later. I want to go for some kernels, and we'll talk about bias variance probably on Wednesday. Yeah. I think the no free lunch theorem is a fascinating theoretical concept, but I think that it's been, I don't know, it's been less useful actually, because I think we have inductive biases that turn out to be useful. There's a famous theorem in learning theory called no free lunch. It was like 20 years ago. That basically says that in the worst case, learning algorithms do not work. For any learning algorithm, I can come up with some data distribution so that your learning algorithm sucks. That's roughly the no free lunch theorem proved about like 20 years ago. But it turns out most of the time, the universe is not that hostile toward us. So yeah, so that's the learning algorithms turned out okay. All right, let's go through one example of kernels. So for this example, let's say that your original input features was three-dimensional, x1, x2, x3. And let's say I'm going to choose the feature mapping phi of x to be all sort of pairwise monomial terms. So I'm going to choose x1 times x1, x1, x2, x1, x3, x2, x1. Okay, and there are a couple duplicates. Like x1, x3 is equal to x3, x1, but it doesn't write it out this way. And so notice that if x is in Rn, right, then phi of x is in Rn squared, right? So we've gone from three-dimensional features to nine-dimensional, and I'm using small numbers for illustration. In practice, think of x as 1,000-dimensional, and so this is now a million, right? Or think of this as maybe 10,000, and this is now like 100 million. Okay, so n squared features is much bigger. And then similarly, phi of z is going to be z1, 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 z2. Okay. So we've gone from n features, like 10,000 features, to n squared features, which would be, in this case, 100 million features. So because there are n squared elements, right, you would need order n squared time to compute phi of x, or to compute phi of x transpose phi of z explicitly, right? So if you want to compute the inner product between phi of x and phi of z, and you do it explicitly in the obvious way, it'll take n squared time to just compute all of these inner products and then do the, right, and then compute this, right? And it's actually n squared over 2 because a lot of these things are duplicated, but that's still order n squared. But let's see if we can find a better way to do that. So what we want is to write out the kernel of x comma z. So there's phi of x transpose phi of z, right? And what I'm going to prove is that this can be computed as x transpose z squared, right? And the cool thing is that, remember, x is n-dimensional, z is n-dimensional. So x transpose z squared, this is an order n time computation, right? Because taking x transpose z, you know, that's just inner product of two n-dimensional vectors, and then you take that number, x transpose z is a real number, and you just square that number. So that's an order n time computation. And so let me just prove that x transpose z is equal to, well, let me prove this step, right? And so x transpose z squared, that's equal to right, so this is x transpose z, right, and then times this is also x transpose z. So this formula is x transpose z squared. It's x transpose z times itself. Okay. And then if I rearrange sums, this is equal to sum from I equals 1 through n, sum from j equals 1 through n, xi, zi, xj, zj. And this, in turn, is, you know, sum over I, sum over j of xi, xj times zi, zj, right? And so what this is doing is it's marching through all possible pairs of I and j and multiplying xi, xj with the corresponding zi, zj and adding that up. But of course, if you were to compute phi of x transpose phi of z, what you do is you take this and multiply it with that, and then add it to the sum, then take this and multiply it with that and add it to the sum, and so on until you end up taking this and multiplying that and adding it to your sum, right? So that's why, this formula is just, marching down these two lists and multiply, and add it up, which is exactly phi transpose, which is exactly phi of x transpose phi of z. Okay, so this proves that you've turned what was previously an order n squared time calculation into an order n time calculation, which means that if n was 10,000, instead of needing to manipulate 100,000 dimensional vectors to come up with these, oh, this is my phone buzzing, this is really loud. Okay, instead of needing to manipulate sort of 100,000 dimensional vectors, you could do so manipulating only 10,000 dimensional vectors. Now, a few other examples of kernels. It turns out that if you choose this kernel, so let's see, we had k of x comma z equals x transpose z squared. If we now add a plus c there, where c is a constant, so c is just some fixed real number, that corresponds to modifying your features as follows. Where instead of just this, binomial terms, pairs of these things, if you add plus c there, it corresponds to adding x1, x2, x3 to your set of features. Technically, there's actually a weighting on this. There's actually root 2c, root 2c, root 2c, and then adds a constant c there as well. You could prove this yourself, but it turns out that if this is your new definition for phi of x, and make the same change to phi of z, so root 2c, z1, and so on, then if you take the inner product of these, then it can be computed as this, right? And so that's, and so the row of the constant c, it trades off the relative weighting between the binomial terms, the xi, xj, compared to the first degree terms, like x1 or x2 or x3. Other examples, if you choose this, to the power of d, right? Notice that this still is an order n time computation, right? X transpose z takes order n time, you add a number to it, and you take this to the power of d, so you can compute this in order n time. But this corresponds to now phi of x has all, the number of terms turns out to be n plus d, choose d, but it doesn't matter. It turns out this contains all features of monomials up to order d. So by which I mean, if let's say d is equal to 5, right? Then this contains, then phi of x contains all the features of the form x1, x2, x5, x17, x29, right? This is a fifth degree thing, or x1, x2 squared, x3, x 18. This is also a fifth order polynomial, fifth order monomial is called. And so if you choose this as a kernel, this corresponds to constructing phi of x to contain all of these features, and there are kind of exponentially many of them, right? There are a lot of these features. These are called monomials. Basically, all the polynomial terms, all the monomial terms, up to a fifth degree polynomial, up to a fifth order monomial term. So, and it turns out there are n plus d choose d, which is roughly n plus d to the power of d, very roughly. So this is a very, very large number of features. But your computation doesn't blow up exponentially, even as d increases. Okay. So what the support vector machine is taking the optimal margin classifier that we derived earlier and applying the kernel trick to it. in which we already had the, so optimal margin classifier. Plus the kernel trick, right? That is the support vector machine. Okay. And so if you choose some of these kernels, for example, then you could run an SVM in these very, very high dimensional feature spaces, in these 100 trillion dimensional feature spaces, but your computational time scales only linearly as order n, as a dimension of your input features x, rather than as a function of this 100 trillion dimensional feature space you're actually building a linear classifier in. Okay? So why is this a good idea? Let me just finish. Oh, right. I'm going to show a quick video to give you intuition for what this is doing. Let's see. Okay, I think projector takes a while to warm up, does it? All right. Any questions while we're, yeah? Yes. So this kernel function applies only to this feature mapping. So each kernel function, yes, up to trivial differences, right? If you have a feature mapping where the features are permuted or something, then the kernel function stays the same. So there are trivial transformations like that, but if you have a totally different feature mapping, you would expect to need a totally different kernel function. Yeah. Cool. So I wanted to, let's see. Oh, cool, awesome. I want to give you a visual picture of what this all right. This is a YouTube video that Ken Katan-Farouche, who teaches CS230, found and such as I use. So I don't know who Udi Aharoni is, but this is a nice visualization of what a support vector machine is doing. So let's say you have a learning algorithm where you're trying to separate the blue dots from the red dots, right? So the blue and the red dots can't be separated by a straight line, but you put them on a plane, and you use a feature mapping phi to throw these points into a much higher dimensional space. So it's now throwing these points in the three-dimensional space. In this three-dimensional space, you can then find W. So W is now three-dimensional because applying the optimal margin classifier in this three-dimensional space that separates the blue dots and the red dots. And if you now examine what this is doing back in the original space, then your linear classifier actually defines that elliptical decision boundary. Does that make sense? Right? So you're taking the data, all right. So you're taking the data, mapping it to a much higher dimensional feature space. 3-dimensional is visualization, but in practice can be 100 trillion dimensions. And then finding a linear decision boundary in that 100 trillion dimensional space, which is going to be a hyperplane, like a straight, like a plane or a straight line or a plane. And then when you look at what you just did in the original feature space, you found a very nonlinear decision boundary. Okay. So this is why, and again, you can only visualize relatively low dimensional feature spaces, even on a display like that. But you find that if you use a SVM kernel, right, you could learn very nonlinear decision boundaries like that. But that is a linear decision boundary in a very high dimensional space. But when you project it back down to 2D, you end up with a very nonlinear decision boundary like that. Okay? All right. So, yeah. Oh, sure, yes. So in this high-dimensional space represented by the feature mapping phi of x, does the data always have to be linearly separable? So far, I've been pretending that it does. I'll come back and fix that assumption later today. Yeah. Okay, so now, how do you make kernels? Right. So here's some intuition you might have about kernels. If x and z are similar, you know, if two input examples x and z are close to each other or similar to each other, then k of xz, which is the inner product between x and z, right? Presumably, this should be large. And conversely, if x and z are dissimilar, then k of xz, you know, this maybe should be small, right? Because the inner product of two very similar vectors that are pointing in the same direction should be large, and the inner product of two dissimilar vectors should be small, right? So this is one guiding principle behind, you know, what you see in a lot of kernels. Just if this is phi of x and this is phi of z, the inner product is large, but if they kind of point off in random directions, the inner product will be small, right? That's how vector inner product works. And so, well, what if you just pull a function out of the straight air, out of the air, which is k of xz equals e to the negative x minus z squared over 2 sigma squared, right? So this is one example of a similarity. If you think of kernels as a similarity measure of function, this, you know, let's just make up another similarity measure of function. And this does have the property that if x and z are very close to each other, then this would be e to the 0, which is about 1. But if x and z are very far apart, then this would be small, right? So this function, it actually satisfies this criteria. It satisfies those criteria. And the question is it okay to use this as a kernel function, right? So it turns out that a function like that, k of xz, you can use it as a kernel function only if there exists some phi such that k of xz equals phi of x transpose phi of z, right? So we derived the whole algorithm assuming this to be true, and it turns out if you plug in the kernel function for which, you know, this isn't true, then all of the derivation we wrote down breaks down, and the optimization problem, you know, can have very strange solutions, right? That don't correspond to good classification, a good classifier at all. And so this puts some constraints on what kernel functions we could choose. For example, one thing it must satisfy is k of xx, which is phi of x transpose phi of z. This had better be greater than or equal to 0, right? Sorry. Right? Because inner product of a vector with itself had better be non-negative. So if k of xx is ever 0 or less than 0, then this is not a valid kernel function. Okay? More generally, there's a theorem that proves when is something a valid kernel. So let me just outline that proof very briefly, which is let's set x1 up to xd, you know, be any d points, right? And let's let k, sorry about overloading of notation. This is, so k represents a kernel function, and I'm going to use k to represent a kernel matrix as well. Sometimes it's also called the grand matrix, but it's called the kernel matrix. So that kij is equal to the kernel function applied to two of those points, xi and xj, right? So you have d points, so just apply the kernel function to every pair of those points and put them in a matrix, in a big d by d matrix like that. So it turns out that given any vector z, and I think you've seen something similar to this in problem set 1, but given any vector z, z transpose kz, which is sum over I, sum over j, zi, kij, zj, right? If k is a valid kernel function, so if there is some feature mapping phi, then this should be equal to sum over I, sum over j, zi, phi of xi transpose phi of z xj times zj. And by a couple other steps, let's see, this phi of xi transpose phi of xj, I'm going to expand out that inner product. So sum over k phi of xi element k times phi of xj element k times zj. And then rearranging sums is sum over k. Actually, sorry, I'm running out of whiteboard. I'll just do it on the export. So rearrange sums, sum over k, sum over I, sum over j, zi, phi of xi, subscript k, times phi of xj, subscript k, times zj, which is sum over k squared, and therefore this must be greater than or equal to 0. Right? And so this proves that the matrix K, the kernel matrix K, is positive semi-definite. Okay? And so more generally, it turns out that this is also a sufficient condition for a kernel function, for a function K to be a valid kernel function. So let me just write this out. This is called a Mercer's theorem, M-E-R-C-E-R. Right. So K is a valid kernel So K is a valid kernel function, i.e. there exists phi such that K of xz equals phi of x transpose phi of z if and only if for any d points, x1 up to xd, the corresponding kernel matrix is a positive semi-definite, so write as k greater than or equal to 0. And I proved just one dimension, one direction of this implication, right? This proof outline here shows that if it is a valid kernel function, then this is positive semi-definite. This outline didn't prove the opposite direction. It's this if and only if, right? Shows both directions. So this algebra we did just now proves that dimension of the proof. I didn't prove the reverse dimension, but this turns out to be a if and only if condition. And so this gives maybe one test for whether or not something is a valid kernel function. Okay? And it turns out that the kernel I wrote up there, that one, k of xz, right? It turns out this is a valid kernel. This is called the Gaussian kernel. This is probably the most widely used kernel. Actually, let me. Well, Actually, the most widely used kernel is maybe the linear kernel, which just uses k of xz equals x transpose z. And so this is using, phi of x equals x, right? So no high dimensional features. So sometimes you call it the linear kernel. It just means you're not using a high dimensional feature mapping, or the feature mapping is just equal to the original features. This is actually a pretty commonly used kernel function. You're not taking advantage of kernels, in other words. But after the linear kernel, the Gaussian kernel is probably the most widely used kernel, the one I wrote up there. And this corresponds to a feature dimensional space that is infinite dimensional, right? And this particular kernel function corresponds to using all monomial features. So if you have x1 and also x1 x2 and x1 squared x2 and x1 squared x5 to the 10 and so on, up to x1 to the 10,000 and x2 to the 17, right? Whatever. So this particular kernel corresponds to using all these polynomial features without n, going to arbitrarily high dimensional, but giving a smaller weighting to the very, very high dimensional ones, which is why yeah. Okay. Great. So the kernel, and toward the end, I'll give some other examples of kernels. So it turns out that the kernel trick is more general than the support vector machine. It was really popularized by the support vector machine, where researchers, I guess Vladimir Vatnik and Coronel Cortez, found that applying this kernel trick to support vector machine makes for a very effective learning algorithm. But the kernel trick is actually more general. And if you have any learning algorithm that you can write in terms of inner products like this, then you can apply the kernel trick to it. And so you play with this for a different learning algorithm in the program assignments as well. Right? And the way to apply the kernel trick is take a learning algorithm, write the whole thing in terms of inner products, and then replace it with k of xz for some appropriately chosen kernel function k of xz. And all of the discriminative learning algorithms we've learned so far can be written in this way, so they can apply the kernel trick. So linear regression, logistic regression, everything in the generalized linear model family, the perceptron algorithm, all of those algorithms, you can actually apply the kernel trick to, which means that you can apply linear regression in an infinite dimensional feature space if you wish. And later in this class, we'll talk about principal components analysis, which you heard of. But when we talk about principal components analysis, turns out that's yet another algorithm that can be written only in terms of inner products. And so there's an algorithm called kernel PCA, kernel principal components analysis. If you don't know what PCA is, don't worry about it. We'll get to it later. But a lot of algorithms can be married with the kernel trick to implicitly apply the algorithm in even an infinite dimensional feature space, but without needing a computer to have an infinite amount of memory or using an infinite amount of computation. But this, actually, the single place that's most powerfully applied is the support vector machine. In practice, the kernel trick is applied all the time in support vector machines and less often in other algorithms. All right. Actually, any questions? No? Okay. All right. So last two things I want to do today. One is fix the assumption that we had made that the data is linearly separable. Right? So, sometimes you don't want your learning algorithm to have 0 errors on the training set, right? So when you take this low-dimensional data and map it to a very high-dimensional feature space, the data does become much more separable. But it turns out that if your data set is a little bit noisy, if your data looks like this, you maybe wanted to find a decision boundary like that, and you don't want it to try so hard to separate every little example, right, as to find a really complicated decision boundary like that, right? So sometimes either in the low-dimensional space or in the high-dimensional space phi, you don't actually want the algorithm to separate out your data perfectly, and then sometimes even in a high-dimensional feature space, your data may not be linearly separable, and you don't want the algorithm to have zero error on the training set. And so there's an algorithm called the L1 norm soft margin SVM, which is a modification to the basic algorithm. So the basic algorithm was min over this, right, subject to okay. And so what the L1 norm soft margin does is the following. It says, previously this is saying that, so remember this is the geometric margin. Right? If you normalize this by the norm of W, it becomes, excuse me, this is the functional margin. If you divide this by the norm of W, it becomes the geometric margin. So this optimization problem was saying, let's make sure each example has functional margin greater than or equal to 1. And in the L1 norm soft margin SVM, we're going to relax this. We're going to say that this needs to be bigger than 1 minus C. There's a Greek alphabet C. And then we're going to modify the cost function as follows, where these CIs are greater than or equal to 0. Okay? So remember, if the functional margin is greater than or equal to 0, it means the algorithm is classifying that example correctly, right? So long as this thing is greater than or equal to 0, then y and this thing will have the same sign, either both positive or both negative. That's what it means. For a product of two things to be greater than 0, both things have to do the same sign, right? And so if this is so long as this is bigger than 0, it means it's classifying that example correctly. And the SVM is asking for it to not just classify it correctly, but classify it correctly with a functional margin of at least 1. And if you allow CI to be positive, then that's relaxing that constraint. Okay? But you don't want the CIs to be too big, which is why you add to the optimization cost function a cost for making CI too big. And so you optimize this as a function of W, B, and these Greek alphabets, C. And if you draw a picture, it turns out that in this example, with that being the optimal decision boundary, it turns out that these examples, these three examples will be equidistant from this straight line, right? Because if they weren't, then you could fiddle the straight line to improve the margin even a little bit more. It turns out that these three examples have functional margin exactly equal to 1. And this example over there will have functional margin equal to 2. And the further away examples have even bigger functional margins. And what this optimization objective is saying that is okay if you have the example here with functional margin. So everything, right, so everything here has functional margin 1. If an example here will have functional margin a little bit less than 1, and this by setting CI to 0.5, say, is letting you get away with having functional margin a little bit less than 1. And one other reason why you might want to use the L1 norm soft margin SVM is the following, which is, let's say you have a data set that looks like this. It seems like that would be a pretty good decision boundary, right? But if we add just, maybe a lot of examples, there's a lot of evidence, but if you have just one outlier, say over here, then technically the data set is still linearly separable. right? If you really want to separate this data set, sorry, I seem to be killing these pens myself as well. All right. If you want to separate out this data set, you can actually, choose that decision boundary. But the basic optimal margin classifier will allow the presence of one training example to cause you to have this dramatic swing in the position of the decision boundary. So because the original optimal margin classifier, it optimizes for the worst case margin, the concept of optimizing for the worst case margin allows one example, by being the worst case training example, to have a huge impact on your decision boundary. And so the L1 non-soft margin SVM allows the SVM to still keep the decision boundary closer to the blue line, even when there's one outlier, and it makes it much more robust to outliers. Okay. And then if you go through the representative theorem derivation, represent W as a function of the alphas and so on, it turns out that the problem then simplifies to the following. So this is, I'm just, oops. Right, after after the whole representative calculation, derivation. This is just what we had previously. I've not changed anything so far. Right, this is just exactly what we had. Right, and it turns out that the only change to this is we end up with an additional condition on the alpha rise. So if you go through that simplification, now that you've changed the algorithm to have this extra term, then the new form, this is called the dual form or the optimization problem. The only change is that you end up with this additional condition. Right? The constraints between alpha are between 0 and C. And it turns out that today there are very good, packages, software packages for just solving that for you. I think once upon a time, we were doing machine learning, you need to worry about whether your code for inverting matrices was good enough, right? When code for inverting matrices was less mature, there's just one thing you have to think about. But today, linear algebra, packages have gotten good enough that when you invert a matrix, you just invert the matrix. You don't have to worry too much. When you solve it, you don't have to worry too much about it. So in the early days of SVM, solving this problem was really hard. You had to worry if your optimization package is optimizing it. But I think today, they're very good numerical optimization packages. They just solve this problem for you, and you can just call it without worrying about the details that much. All right, so this L1 non-soft margin SVM, and so this parameter C is something you need to choose. We'll talk on Wednesday about how to choose this parameter, but it trades off how much you want to insist on getting the training examples right versus, saying it's okay if you label a few training examples wrong. We'll discuss on Wednesday when we discuss bias and variance, how to choose a parameter like C. Okay. All right. So the last thing I'd like you to see today is just a few examples of SVM kernels. Let me just give, all right. So it turns out the SVM with a polynomial kernel works quite well. So this is, K of x z equals x transpose z to the d. This is sometimes called a polynomial kernel. And this is called a Gaussian kernel. It's really the most widely used one is a Gaussian kernel, right? And it turns out that, I guess, early days of SVMs, one of the proof points for SVMs was the field of machine learning was doing a lot of work on handwritten digit classification. So a digit is a matrix of pixels with values that are, 0 or 1 or maybe grayscale values. Right? And so if you take a list of pixel intensity values and list them, so this is 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 1, 0, and just list out all the pixel intensity values, then this can be your feature X, and if you feed it to an SVM using either of these kernels, it'll do not too badly as a handwritten digit classification, right? So there's a classic data set called MNIST, which is a classic benchmark in history of machine learning. And it was a very surprising result many years ago that, support vector machine with a kernel like this does very well on handwritten digit classification. In the past several years, we found that deep learning algorithms, specifically convolutional neural networks, do even better than the SVM. But for some time, SVMs were the best algorithm. And they're very easy to use in turnkey. There aren't a lot of parameters to fiddle with. So that's the one very nice property about them. But more generally, a lot of the most innovative work in SVMs has been in the design of kernels. So here's one example. Let's say you want a protein sequence classifier. Right. So protein sequences are made up of amino acids. So I guess a lot of our bodies are made of proteins, and proteins are just sequences of amino acids. And there are 20 amino acids. But in order to simplify the description and really not worry too much about biology and hope the biologists don't get mad at me, I'm going to pretend there are 26 amino acids, even though because there are 26 alphabets. So I'm going to use the alphabets A through Z to denote amino acids, even though I know there's supposed to be only 20, but it's just easier to talk with 26 alphabets. And so a protein is a sequence of alphabets right? Because a protein in your body is made up of a sequence of amino acids. And amino acids can be very variable length. Some can be very, very long, some can be very, very short. So the question is, how do you represent the feature X? So it turns out, so the goal is to be able to input X and make a prediction about this particular protein, like what is the function of this protein, right? And so, well, here's one way to design a feature vector, which is I'm going to list out all combinations of 4 amino acids. You can tell this will take a while, right? Go down to A, Z, and then A, B, A, and so on. And eventually, there'll be a BA, JT, TSTA, down to ZZZZ, right? And then I'm going to construct phi of X according to the number of times I see this sequence in the amino acid. So for example, BAJT appears twice, so I'm going to put 2 there. TSTA, whatever, right, appears once, so I'm going to put a 1 there, and there are no AAAs, no AABs, no AACs, and so on. Okay, so this is a 20 to the 4, 26 to the 4, 20 to the 4 dimensional feature vector. So this is a very, very high dimensional feature vector. And it turns out that using, so this is 20 to the 4 is 160,000. It's pretty high dimensional, quite expensive to compute. And it turns out that using dynamic programming, given 2 amino acid sequences, you can compute 5x transpose phi of z as k of xz. And there's a dynamic programming algorithm for doing this. The details aren't important for purposes of CS229. If any of you have taken an advanced CS algorithms course and learned about the Knuth-Morris-Pratt algorithm, it's quite similar to that. So Don Knuth, right, was Stanford professor, emeritus professor here. So the DP algorithm is quite similar to that. And using this is actually this is actually a pretty decent algorithm for inputting a sequence of, say, amino acids and training a supervised learning algorithm to make a binary classification on amino acid sequences. Okay? So as you apply support vector machines, one of the things you see is that depending on the input data you have, there can be innovative kernels to use in order to measure the similarity of 2 amino acid sequences or the similarity of 2 of whatever else, and then to use that to build a classifier, even on very strange shaped objects, which do not come as a feature. Okay. So, and I think actually another example, if the input X is a histogram, maybe you have two different countries, you have histograms of people's demographics. It turns out that there is a kernel that taking the min of the two histograms and then summing up to compute a kernel function that inputs two histograms and measures how similar they are. So there are many different kernel functions for many different unique types of inputs you might want to classify. Okay? So that's with SVMs, very useful algorithm, and what we'll do on Wednesday is continue with more advice on, now that you know all of these learning algorithms, we'll talk about bias and variance to give you more advice on how to actually apply them. So let's break, and then look forward to seeing you on Wednesday.